Hi, y'all. So we are going to start chapter four. Chapter four is all about forces in motion and specifically Newton's laws. So a couple of things that we're going to be going through, well, forces, Newton's three laws, and also something called free body diagrams that are going to help us to basically lay out, kind of sketch out how forces act on an object. And uh, ends up giving us a vector picture that helps us in problem solving. Okay, so before we get started on that, though, we have to talk about the concept of mass. And mass is really, what is mass? Mass is a measure of how much stuff is actually in an object. So we tend to get this twisted up a little bit, and we tend to, or we can accidentally try to use mass and weight interchangeably, and they're really not the same thing. Um, this gets more confusing for us because of the fact that well, we're in the United States, and we use pounds to measure weight, and then we think that well, kilograms and pounds are just interchangeable by a little factor of 2.2 pounds per kilogram, but really kilograms are a unit of mass and pounds are a unit of weight, and so it's a little bit confusing for us. But if we stick with the SI units of kilograms, a lot of the confusion kind of naturally goes away, and we'll talk about weight later on in chapter 4. All right. So what is it exactly that mass measures besides just the amount of stuff? Well, an object's mass kind of gives us an idea of how much inertia it has. And inertia is just resistance to change in motion. And the larger something's mass is, the more inertia it has, the more resistant it's going to be to a change in its motion. All right. So what's a force? Well, a force is just a push or a pull, and well, force has direction to it. Um, if I push on you, you're going to feel the force being directed towards you and away from me. Force is a vector because, well, force has direction. There are two general types of forces. There's contact forces, which, well, are due to physical contact, which I guess makes sense. And then there's long-range forces. And long-range forces are things like gravity and electrical forces. In first semester physics, the only long-range force we deal with is gravity. Everything else is a contact force. So for instance, me pushing on you, or maybe the floor pushing on me as I stand up, or the chair pushing on me as I sit here. Or friction, or air resistance, which we sometimes call drag, tension, um, buoyancy. Those are all contact forces. The only long-range force we have is gravity. Now, the SI unit of force is the Newton. It's right there, and a Newton literally is a kilogram meter per second squared. All right. Newton's first law says that if an object is at rest, it's going to stay at rest. If an object is in motion, it's going to stay in motion unless that object is acted upon by some net force. Okay. So if I've got an object that's just cruising along happily, and it doesn't have a net force acting on it, then it's going to continue to cruise along happily. Or if it's just sitting there happily and it doesn't have a net force acting on it, it's just going to continue to sit there happily. What's net force mean? That means that I've got basically unbalanced forces that are acting on an object. So basically, I look at all the forces acting on an object, I sum them all up according to the X and Y directions, and if they don't exactly balance out, then I'm going to have a net force acting on my object. Right. So that's exactly what I just said, right? The net force is what? It's the vector sum of all the forces acting on an object. All right. So for instance, I could have my two kids here. They're pulling on the candy, And maybe the girl is pulling with 5 newtons of force to the right, and the boy is pulling with 3 newtons of force to the left. And you notice what I did with the vector sizes there. I made them match up, or at least I tried to make them match up with the sizes of the forces. Then my net force, that's a little sum sign. The sum of my forces in my x direction here would be 5 newtons minus 3 newtons, 5 newtons to the right, and then 3 newtons to the left, so that's my negative direction, equals 2 newtons. And that would be my total force acting on my candy, I guess, when the girl's pulling really hard and the boy's not pulling quite as hard. Okay, so that was Newton's first law. A bunch of words. Newton's second law is really just an equation, and it says that, well, my net force is equal to mass times acceleration. So this Greek letter there, that's a Greek letter sigma. That's just notation to say that I'm adding all my forces together. So this says the sum of the forces is equal to mass times acceleration. And what I can do is I can break this into x and y components so that the sum of all my forces, sum of all the x part of my forces is equal to mass times acceleration in the x direction. And the sum of all the y parts of my forces is equal to mass times acceleration in the y direction. Just like we did with kinematics in 2D, we broke it up into x and y directions. We can do the same thing when we start talking about forces. All right, so that's Newton's second law. This is going to be our powerhouse that we're going to use a lot in this chapter in order to solve problems. All right, what about Newton's third law? Well, Newton's third law says that if I've got 2 objects, and object A here acts on object B with some force, then object B is going to act back on object A with the exact same size force, but in the opposite direction. And this could be, 2 kids. This could be me pushing against John Cena. And John Cena could push back on me, and you guys will say, well, John Cena is a lot stronger than you, Dr. Houston. I'll say, yeah, he is. But still, Newton's third law says that if he pushes on me with some force, then my body is pushing back on him with the exact same size force in the opposite direction. Which is a little confusing to think about, but it becomes a little bit clearer once we do some example problems and put some numbers to this. All right, that's all I have. I will talk to you guys later on, and we'll do some example problems over a lot of this stuff, and it'll become clearer. Okay, all right, bye. No, really, bye.